8 minutes. Within 8 minutes, you will complete, and next 2 minutes we will discuss. Please.
Okay. Good evening to all. Thanks to the Physical Society for giving such a platform to present our research work. I am Mohammad Alfad Hussain from Physics-2021 University. On behalf of our research team, we'll present our study titled Comparison of Structural and Magnetic Characteristics of Cobalt Nickel Ferrite at Functionalized CNT's Nanocomposite, synthesized by different routes of hydrothermal process. Before diving into the details, I would like you to get acquainted with the outline of today's presentation. I will commence the presentation with a little introduction of this research work, followed by research methodology, results analysis, and eventually the conclusion. To begin with the introduction, I would like to share the motivation behind the study. Due to the rapid increment of industries around the globe, the disposal of wastewater is being a headache for industrial companies and nations. To have environmentally safe surroundings, the toxic component in the wastewater are needed to be eliminated. So carbon is used as commercial adsorbent. However, due to the limited availability, low absorption capacity, and difficult recovery problems, it seems not feasible to use. Recently, attention has been focused on the application of nanostructured materials as adsorbents. Due to the hollow and layer structure and large specific surface area, CNT is becoming an excellent candidate as an adsorbent. There are two types of CNT. One is single wall nanotubes and another is multi-wall nanotubes. We work with multi nanotubes in this study. On the other hand, another constituent of this study, ferrites possess various electrical and magnetic properties. So the objective of our research was to synthesize structurally and magnetically finely tuned nanocomposite engendered from CNT and ferrite that can be used in wastewater treatment. So turn on to the research methodology. These are the raw materials we used in our research. Multi-wall carbon nanotubes was prepared through CVD process and we added them to a 3:1 volume ratio of sulfuric and nitric acid mixture. Then the mixture was sonicated and acid refluxed for a particular time. The nickel substituted cobalt ferrite, which we are calling cobalt nickel ferrite, was prepared by hydrothermal method as shown in this picture. To synthesize the nanocomposite, two different routes were chosen. First one was adding the ferrite particle and functionalized CNT separately, and second one was the in situ growth of ferrite particle on functionalized CNT matrix. Both of these routes were governed by the hydrothermal method. From now on, we will denote composite from separate addition as S composites and in situ growth as I composite. Now, go to the result and analysis. We are starting with the Xrd analysis. In this figure, A shows the Xrd for pristine CNT and B shows the Xrd patterns for functionalized CNT. As we can see, after functionalization process, the characteristics peak of CNT, which is 002 plane, shifted towards lower angle. This shifting is attributed to the insertion of functionalized group at the edge of each layer. From the curve of C, we can see the Xrd for ferrite, and we can confirm the formation of inverse final structure as per the curve. Because we see the Miller indices of the lattice plane either odd or even. There is no extra peak related to impurities exist there. So we can conclude that the prepared sample are highly pure. From the Xrds of nanocomposite, we can see all the nanocomposites have same lattice plane as ferrite, but S composites have an additional plane 002, which is corresponding to the functionalized nanotube. We can say this indicates the formation of nanocomposite, but there are some unreacted tube which contributed to this. On the other hand, no evident diffraction peaks of functionalized CNTs were observed for I composite, as we can see in figure F and J. This may be attributed to the strong interferential bonding between the ferrite nanoparticles and the functionalized nanotube. Because ferrite nanoparticle has grown on the surface of functionalized nanotube. And we also observe the prominent peak of ferrite reduced in height of Xrd of the nanocomposite. This may be due to the decrease in crystallinity. Now, if we see the most prominent peak for 311, which is the 311 plane, we can see there are two effects on increasing the percentage of nanotube in the composition. First one is the shift of the peak, and second one is the peak broadening. Peaks of I composite were moved to higher theta angles, than that of S composite, as well as greater peak broadening. This suggests that nanotubes have bonded more firmly with smaller crystallized size for I composite. In comparison between S and I composites, the diffraction pattern indicates that nanotubes had incorporated the ferrite more delicately for I composites. And now the Debye-Shira formula, as we can see, we calculated the crystallite size, and we can see the crystallite size of nanocomposite is lower than the crystallite size of ferrite nanoparticles. The lattice constant was calculated theoretically using the formula for cubic structure in this slide, and with the help of Nilsson function, we also found the lattice constant, and we can compare these two data and see that these two data are almost same. Using the Williamson-Hall method, the WH method, the micro strains of nanocomposite were calculated. We calculated this to see actually how much broadening is induced due to the crystallite size and how much broadening is induced due to the strain. Now move on to the Raman analysis. The Raman analysis, as we can see in this picture, now Raman analysis for carbon nanotubes shows the characteristics D and G. After functionalization, the intensity ratio of D and G band increased, which confirmed the functionalization of multi-wall carbon nanotube. Because D band is correspondent to the disorder and effects of CNT, where G is associated with the graphitic structure of nanotubes. Moreover, the Raman spectra of pristine CNT showed relatively ample noise, as we can see in curve A, than that of functionalized CNT, as we can see in curve B. This much noise in curve A may be engendered from the fluorescence originating from the residual metal impurities, which was mainly which can be occurred during the preparation of this CNT. The less fluorescence observed in the curve B indicates the concentration of impurities lowered with the acid reflux treatment. The rise of G prime band, as we can see, indicates this G prime band intensity rise indicates that the bundlement of layers of multiple. Now, if we can move to the composite Raman spectrum, we taken for one the FCI11 composite. This, along with the D and G band, the spectrum shows two less prominent bands at lower wave number range. The bands are 469 centimeter inverse 1 and 687 centimeter inverse 1 are assigned to the tetra and octahedral side respectively. This due to the inverse nature of ferrite nanoparticles. This spectrum indicates that the ferrite nanoparticles.
You have 2 minutes left.
Okay. With the multiple matrix and plentiful fluorescence throughout the curve indicates the presence of abundant metal elements in the composite. Now move on to FTR analysis. From the FTR analysis, we can confirm the functional groups of our pristine CNT and functionalized CNT. In the FTR cup for pristine CNT, we can see bands corresponding to OH stretching vibration, CH stretching vibration for asymmetric and symmetric both, C double bond O vibration, CO stretching vibration, and C double bond stretching vibration. After functionalization, except C double bond vibration, all of the band's intensity increased. The reduced C double bond indicates a strong oxidation has taken place, which is indicative of defects on the nanotube structure. From the in this figure, from the FTR of CNF, we can see two characteristics band appeared at 400 and 600 centimeter inverse 1 regime. The lower wave number band was associated with the octahedral side, and the higher wave number range was associated with the tetrahedral side. Now we can see the nanocomposite consists of all bands, with including ferrite and nanotubes FTR band. So peaks ranging with 1400 centimeter inverse 1 and 190 centimeter inverse 1 are coming in not prominently, but with the increasing functionalized CNT amount, since all of those related to functionalized CNT. It is seen that the intensity of characteristic of ferrite is decreased with the increased amount of functionalized tube in composite. It may be attributed to the nanotubes form well bond with ferrite nanoparticles. This can see in all of the nanocomposite curve. Now, with the introduction and augmentation of the functionalized CNT and CNT, the absorption band at 400 centimeter range got splitted and become doublet. This is due to the two cation existence at octahedral site. If we if we study the TGA curve for all of this sample, we can see the CNF has the higher thermal stability, and after mixing the nanotubes and the ferrite nanoparticles, we can see or we can conclude the composite synthesis via in situ growth technique is far more thermally stable than composite prepared as separately added and mixing route. From this TGA study, we can say that synthesis route, constituent amount, and bond linking between constituent for different groups influence the thermal behavior of nanocomposite. Now, if we, as we study the magnetic properties, the image curve for functionalized CNT indicate that the nanotube possesses ferromagnetic nature with the saturation magnetization, remnant magnetization, and porosity are present there, as you can see in the black one. This ferromagnetic nature really originated from the metal catalyst used for CNT synthesis. The magnetic nature of the ferrite nanoparticle demonstrated the S saturation magnetization and remnant magnetization among all the samples. All the magnetic parameters are tabulated in this table. As we can see from the magnetic study, it is evident that the grafting of ferrite nanoparticle on low magnetic functionalized nanotube matrix influence the magnetic parameters. The
if time is finished, please conclude as early as possible.
Just 1 minute. The reduced magnetization of the composite can be ascribed to the presence of disordered spin on the surface of nanotubes, where the ferrite particle to the increase in surface to volume ratio. This can also be one of the reasons for reduced saturation magnetization. The irregularity case of coercivity can be assigned to the different factors like particle size, different kinds of domain formation, ferrite nanotube content ratio, magnetic crystalline anisotropy, etc. Now we can conclude that the adhesion is greater in situ growth composite compared to S composites. Crystallite size and strain of the composite are influenced by the route of synthesis. In I composites show greater saturation magnetization, better thermal stability counter particles. The amount of carbon nanotube in composite affects the thermal stability. As we prepared this sample mainly for wastewater treatment, but after studying the literature and seeing properties, seeing and analyzing the properties of our sample, we are very much happy to express the future scope of this material in field of drug delivery, MRI contrast agent, energy application, and catalysts. To conclude my speech, I would convey my gratitude and acknowledgement for the support of Physics Discipline, Pune University, and Material Science Division, Atomic Energy Center, Dhaka. Thank you for your patience.
Okay. Thank you very much, Mr. Fahad, for your nice presentation. So we are again constrained with time. So only one question is encouraged. Only one question.
Sir, Dr. Basit is here.
Okay.
Okay, sir. There is no other. So just one question. Can you please go to the title of your talk? You have written at the end of the title by different routes of hydrothermal process. So I didn't find any different route of hydrothermal process. My first thing is. Second thing is, when you will work with the hydrothermal treatment, by hydrothermal technique, you must mention the hydrothermal reaction temperature, because all the properties, actually all the phase function, highly dependent on the reaction temperature. So I never found that you mentioned the reaction temperature. This is suggestion, not question actually. The first thing, there is a relationship between your talk and title. So something wrong in the title. I think you have to change the title. Sorry, for your future actually. Second thing is that you must mention the hydrothermal reaction temperature. Third thing, you have measured the crystallite size by Shearer equation. You can only apply Shearer equation, I think, here for the ferrite nanoparticles. First, you need to separate the phase by Rydberg refinement. and then only for the spherical particles, the shear equation would be applicable. For carbon nanotube, actually, I think that there is aspect ratio. There is, it is not spherical. So for the whole composite, I think I have enough doubt whether you can apply shear equation to calculate the crystallite size. So these are just my suggestion to a student, nothing else. Thank you very much for your nice presentation.
Thank you, sir. Thank you for your suggestion.
And
Actually,
it's better to use the image of the composite actually.
due to the COVID-19, we cannot do the TEM of our composite. So there was a little bit problem with that. And
No, we understand it. Just a suggestion. Just a suggestion.
Just by curiosity, that what different routes of hydrothermal process you intend to investigate actually? What different routes?
I have written as we have two routes chosen. As I said, that we separately added, produced the nanoparticles and the functionalized tube, and then we added them separately. And in another routes, as we are mentioning here, that in that case we have just functionalized nanotube, and then we added the raw materials for ferrite nanoparticles in process of in the hydrothermal process to make the composite. Actually, it is the
just to make you confusion free, just I said this is not called the different routes of hydrothermal process. Hydrothermal process is a single route actually. This one-step synthesis technique. So your method addition or something, the recipe is different, the way of adding is different, but hydrothermal routes is actually on one route actually. It is a one-step process.
You are taking the different steps to follow the hydrothermal process.
So
okay,
that is
let's conclude actually, sir. We are running short of time.
Thank you.
Actually, it may be different methods of the thermal process. Maybe, but the temperature, what the Dr. Basid was asking.
Sorry, I forgot to mention that the temperature for the hydrothermal process was 180 degrees centigrade.
180 degrees centigrade. So you use some autoclave, is it so?
Yes, we use autoclave in material science division of Energy Center.
Okay, thank you. So we can go to the next speaker. The next speaker is investigation of copper, cobalt, sulphide and molybdenum disulphide nanoparticles as electrode material for supercapacitor. Sajjad Hassan, Shubroto Dash, Akhtar, Chanchal Kumar and M.A. Basid. So welcome, Mr. Sajjad Hassan.
Am I audible?
And your time start.
Can everyone hear me?
Yes,
we have.
Thank you.
Start.
Good evening. Welcome to my presentation. I'm Sajjad Hassan. I'm from Department of Physics, Bangladesh University of Engineering Technology. Today, I'm going to present my investigation of copper cobalt sulphide emulsion nanocomposite as electrode material for supercapacitor. Before discussing our findings, let's look at what makes supercapacitor so interesting. Basically, supercapacitor is a high capacity energy storage device, but it has some unique features such as high power density, energy density, fast charging, discharging capabilities, and long durability. This unique feature make it suitable for application in automobile, various consumer electronics, energy harvesting, energy recovery system. This wide variety of application made us curious to develop a new type of supercapacitor. Performance of electrode material depends on large surface area, electrochemical activity, high conductivity, and low ion transfer resistance. To meet this criteria, we have chosen copper cobalt sulphide because it has high specific capacitance, tunable morphology, high conductivity, and its electrochemical activity is better than its oxide. But it has a drawback of high agglomeration and electrochemical dissolution. Various research groups overcome this issue in different ways. One of the promising methods is to incorporate a two-dimensional material with copper cobalt sulphide. For this incorporation, we have chosen molybdenum sulphide because it has a large surface area, high specific capacitance, and it acts as a co-catalyst for electrochemical reaction. But it has a disadvantage of low conductivity. Since this composite has never been synthesized and investigated, the possible outcome of this challenging incorporation pursued us to synthesize and investigate it as electrode material. We have taken a facile synthesis technique to produce copper-cobalt sulfide MOS2 nanocomposite. At first, to produce copper-cobalt sulfate, we have mixed stoichiometric amount of nitrate salt of copper, cobalt, and thiourea. Then we transferred it to an autoclave for hydrothermal treatment. In the meanwhile, we ultrasonicated raw MOS2 and mixed it with the synthesized copper-cobalt sulfate and transferred it to autoclave for hydrothermal treatment. The resultant product was washed and dried in vacuum for our further investigation. The crystallinity and the phase purity of the SPPR copper-cobalt sulfate and nanocomposite samples were investigated by Xrd analysis. As shown in this figure, the diffraction pattern of the prepared copper-cobalt sulfate are perfectly matched with the standard pattern of copper-cobalt sulfate. After the addition of molybdenum sulfide, we observed some distinct peak arises. This is due to the these detectable peaks are well indexed to the crystal plane of molybdenum sulfide. This indicates a successful formation of copper-cobalt sulfide molybdenum sulfide nanocomposite. We didn't see any obvious peak due to the impurities, which suggests we have a high purity of the high purity nanocomposite. FTR studies were performed to characterize the functional group of the synthesized samples. For both prepared copper-cobalt sulfide and the nanocomposite, we observed the presence of bond between copper sulfur and cobalt and sulfur. In addition, in nanocomposite, we have found a bond between molybdenum and sulfide and copper, sulfur, and molybdenum. This provides further evidence of bond formation between copper-cobalt sulfide and MOS2. The morphology of the SPPR nanocomposite and copper-cobalt sulfide are investigated via FACM. In this figure, we can see that the prepared copper-cobalt sulfide particles are non-homogeneous and highly agglomerated. On the other hand, nanocomposite in this nanocomposite is homogeneous and agglomerated in this figure. Interestingly, in the inside view, we can see a layered structure of MOS2. This indication an in situ growth of layered molybdenum sulfide nanosheet during the hydrothermal process. This also indicates a successful formation of nanocomposite. For evaluating the electrochemical performance, cyclic voltammetry, galvanoelectric charge discharge, and electrochemical impedance spectroscopy were conducted in 3-electrode system using sodium sulfate solution as electrolyte. This figure present the CV curves of molybdenum sulfide, copper-cobalt sulfide, and the prepared nanocomposite at a constant scan rate. We can see the nanocomposite have a higher current and larger integrated CV area than the other two samples. Also, the quasi-rectangular shape indicates higher conductivity. The larger area also indicates higher charge storage capability of the nanocomposite. This figure shows CV curve of nanocomposite at different scan rate. Interestingly, no significant change occur in the shape of the CV curve during the increase of scan rate. The GCD curve of the MOS2 copper-cobalt sulfide and nanocomposite are shown in this figure. GCD curve of the nanocomposite indicates an excellent cyclic charging and discharging capability, and no significant IR drop indicates a high conductivity. EIS was further used to study the electrochemical behavior of the electrode, and Nyquist plots of molybdenum sulfide, prepared copper-cobalt sulfide, and prepared nanocomposite electrodes are compared in this figure. Generally, molybdenum sulfide and copper-cobalt sulfide and prepared nanocomposite electrode exhibit semicircle behavior at the high frequency region. Nanocomposite electrodes exhibited a smaller semicircle than the other two samples. This verified it has nanocomposite has high ion diffusion rate. The vertical line at low frequency for both molybdenum sulfide and copper-cobalt sulfide has almost the same slope, but nanocomposite showed a higher slope. This also indicates nanocomposite has a high capability of charge storage. The capacitance of molybdenum sulfide, copper-cobalt sulfide, and nanocomposite at various densities were calculated from the discharge time of GCD and compared in this figure. The specific capacitance of copper cobalt sulfate electrode is significantly increased after the incorporation of MOS2. This can be explained by improvement in the crystallinity and synergetic effect between the synergetic effect of copper cobalt sulfate and MOS2. Also, a specific capacitance of the electrode gradually decreases with the increase of current density. This is because active material is not sufficiently involved in the electrochemical reaction at high current density. Power density and energy density are the critical factor in assessing the operational performance of energy storage device. The relationship between power density and energy density is described through radionuclide. Figure shows the radionuclide of molybdenum sulfide here, copper cobalt sulfide, and nanocomposite in comparison to the other energy storage system. As it can be observed, the incorporating of MOS2 with copper cobalt sulfide has remarkably increased the energy density of the copper cobalt sulfate at the same power density. This improvement in conductivity, and high specific capacitance and diffusion rate of ion on the nanocomposite is responsible for such improvement in energy density. Finally, in this work, we have used a facile hydrothermal technique to produce copper cobalt sulfate and copper cobalt sulfate MOS2 with in situ growth of layered MOS2. Cyclic voltammetry and galvanostatic charge discharge reveal high surface charge storage and improved charging and discharging for copper cobalt sulfate MOS2. The specific capacitance and energy density have been found maximum for copper cobalt sulfate MOS2 with low internal resistance and faster ion diffusion rate. In conclusion, integrating a small amount of molybdenum sulfide into copper cobalt sulfate has significantly enhanced its electrochemical performance. Such an enhancement can pave the way for design and manufacture of highly efficient active electrode material for next generation high performance supercapacitor. I would like to acknowledge this institute and department. Thank you for giving me the chance of presenting my work in this prestigious conference.
Okay. Thank you very much, Mr. Shajjat, for your very interesting lecture, and especially I appreciate that such type of structure for supercapacitors. My interest is also for the molybdenum disulphide, a very interesting material from the structural point of view that has a layered structure, and its composites are extremely used in various purposes, not only supercapacitors, even in photocatalytic materials and energy other sectors. So it's a good work. I think this work should be continued future for a more detailed and appropriate characterization. Continue. So it's a good work.
I have actually performed various work of this material.
Yes, I think you have to make a more detailed study with this type of material, because supercapacitors are the very attractive materials for the future days for the energy storage, because now storage of energy is the main issue, that how you can store the energy for subsequent usage. So that is a big challenge for the scientific community. So thank you very much.
Sir, there is a question.
Okay. So let one question be asked. I think we are short with time.
আমি তো হ্যান্ড রেজ করেছি। আমি প্রফেসর রফিকুল ইসলাম, যিনি বিষয়টা উপস্থাপন করেছেন, আমি ধন্যবাদ জানাই। আর স্যার মিস্টার চেয়ারম্যান খুব প্রশংসা করেছেন, আমি তার সাথে একমত এই কাজটি দেখে। আমার কিছু জানার বিষয় ছিল যে সুপার ক্যাপাসিটর যে কনস্ট্রাকশন বা যে স্টাডিগুলো হয়েছে, এখানে টেম্পারেচারের কোনো বালাই দেখছি না। আর স্যার এটা যদি কোনো ইয়াতে যায়, আমরা ব্যবহারিক ক্ষেত্রে যাই, তাহলে এটা ব্যবহার করার জন্য ইনসুলেশনে কি কোনো সমস্যা বা কোনো ধরনের স্টাডি আছে কিনা, এটা জানার ইচ্ছে ছিল। থ্যাংক ইউ
স্যার। আমরা ওই ধরনের মানে টেম্পারেচার বেসিস আমরা কোনো ধরনের স্টাডি এখন করি না অ্যাকচুয়ালি স্যার।
আর এমনি এটা ব্যবহারিক ক্ষেত্রে যদি ইনসুলেশন করা হয়, সেখানে ইনসুলেশনের তো একটা ফ্যাক্টর থাকে, ঠিক আছে, যেহেতু সুপার ক্যাপাসিটর।
Sir, can I supplement something, Professor?
Can
I just supplement something?
Yes.
So thank you, sir. So actually, sir, আমরা room temperature তে করেছি because আমরা application point of view থেকে the room temperature is more desirable. সেকেন্ড থিং, আমরা এটা 3 ইলেকট্রোড সিস্টেমে সেখানে শো করছে, আমরা 2 ইলেকট্রোড সিস্টেমে করেছি এবং সিমেট্রিক সিস্টেমে, এবং এলইডি আমরা ব্যবহারিক একটা ডিভাইস ফেব্রিকেট করে সেই ডিভাইসটা আমরা অলরেডি রান করেছি এই সুপার ক্যাপাসিটর ইউজ করে, এবং এটা যে এনার্জি ব্যাটারি হিসেবে এটা আসলে যে রিলায়েবল এবং এটা পারফেক্টলি এটা রান করে এবং এটা ইউজেবল, এটা আমরা প্র্যাকটিক্যালি শোন করেছি। সো টাইম কনস্ট্যান্টের কারণে সেগুলো দেখাতে পারে নাই। এরকম আরো মনে করো 2-3টা প্রেজেন্টেশন তার আছে আর কি। তো এটা তার এমএসসির কাজ, বাট he go up to the device fabrication and he used the material for in device application. So আমরা আমাদের যে পারপাস গুলো ছিল স্যার সবগুলো ফুলফিল করছে। ইন কেস অফ ডিভাইস we did not feel any problem actually, আপনি যেগুলো মেনশন করতেছেন, বাট এগুলো এগেইন আরো ফার্দার দেখার
দরকার আছে। হ্যাঁ, অবশ্যই
স্টাডি দরকার ডেফিনেটলি।
Can I give one suggestion, Dr. Basit, sir?
Yes, please. Yes, most welcome. Any suggestion?
Just slide number 4. Can you please show the slide number 4? Okay, you did the ultrasonication here, and with this ultrasonication, you just exfoliate the MOS2, and that sheet, directly you're going to you used in the hydrothermal process. So there is a size discrepancy. So if possible, then I would like to suggest you to separate the size, different size with the centrifugation. Then maybe it will give you the good result.
Thank you, Professor. সাজাদ, আমি বলি ম্যামকে আনসারটা আমি দেব। ম্যাম যেহেতু ইয়ে করছেন যে মারিয়াম ম্যাডাম, আসলে হচ্ছে কি প্রথমে আমাদের প্ল্যান ছিল যে এটাকে আলট্রাসনিক্যালি এক্সফোলিয়েটেড করে ন্যানোশিট তৈরি করা, বাট ইন্টারেস্টিং আমরা দেখলাম যে ইনসিচু ফর্ম করা অনেক ভালো এবং ইনসিচুর ফর্মেশনটা অনেক বেশি রিপ্রোডিউসিবল। সো আমি কেন 2টা স্টেপে যাব? একটা সিঙ্গেল স্টেপে যদি হয়ে যায় তাহলে আমি 2টা স্টেপে কেন যাব? তখন আমরা আমাদের রুট চেঞ্জ করলাম, চেঞ্জ করে জাস্ট একটু আলট্রাসনিকেশন দিয়ে আমরা ক্লিন করছি। উই ডিডন্ট ফর্ম দা ন্যানোশিট বাই আলট্রাসনিকেশন, জাস্ট অল্প একটা মিনিটে আমরা জাস্ট ন্যানো যেগুলো বাল্ক MOS2 তাকে আমরা ক্লিন করেছি আলট্রাসনিকেশন দিয়ে। বাট আমরা দেখলাম ইনসিচু গ্রোথটা অনেক ভালো হয় এবং এটা অনেক রিপ্রোডিউসিবল হয়, যার কারণে আমরা আলাদা আলট্রাসনিকেশন স্টেপে যাই না ফর দা ফরমেশন অফ দা ন্যানোশিট অফ MOS2। এটা আমাদেরকে একটা স্টেপ সেভ করে দিছে। So that is another novelty of this work, right? Just by
here, here you are showing that there is a single sheet or two sheet, okay, two layer.
Yes, we are showing that because in the ultrasonication even you can make it monolayer.
Yeah, definitely. It's not possible to.
It's not possible to make the monolayer. So,
but if 15-minute ultrasonication can produce different layer actually.
Actually, it depends on the raw MOS2 actually. What kind of raw MOS2, how much bulk it is you are using it. So we found that if you around 90 minutes, if you do the ultrasonication, then some sheet about 7 to 8 monolayers form. But in this case, interestingly, we found in situ we can do all these things. So if you can do all these things reproducibly in situ, we didn't go into a second step, right? We minimized one step.
আমার একটা ছোট্ট প্রশ্ন এই রিলেটেড যেহেতু আসে গেল। আচ্ছা, আমার একটা যেটা জিনিস যে এই দুটার মাঝে ল্যাটিস প্যারামিটার কত? কপার কোবাল্ট সালফাইডের ল্যাটিস প্যারামিটার কত?
আচ্ছা, you can answer this question.
আচ্ছা, কারণ হচ্ছে দুটো লেয়ারের ইন্টার লেয়ার স্পেসটা কত?
Is mention the spacing between the interlayer spacing.
Actually, interlayer spacing of MS2 before sonication was 0.17 nanometer, and after sonication we found it at 0.21 nanometer.
আচ্ছা, আমার একটা সাজেশন হচ্ছে যে এই ম্যাটেরিয়াল গুলো যদি আরো একটু ভালো ডেভেলপ করতে পারেন, একটা কাজ করেন না কেন, এক্সপিএস করে দেখেন একটু। এবং এক্সপিএস হচ্ছে ইউভি এক্সপিএস অথবা নরমাল এক্সপিএস করেন, করলে আপনারা ইন্টারনাল স্ট্রাকচার আরো পারফেক্টলি গ্রো করতে পারবেন এবং আপনাদের কনফিডেন্স বেড়ে যাবে কাজে।
থ্যাংক ইউ স্যার। আমরা অলরেডি আইআইটি খড়গপুরে মানে এক্সপ্রেস করার জন্য পাঠিয়েছি, বাট সবকিছু করোনা স্টপ করে রেখে দিয়েছে আসলে। So they are not very good.
Even AFM can give you the size also, thickness.
Yes.
Can give you the
এপিএসএম ভালো করে করা এবং এক্সপিএস এর জন্য হয়তো আমি বলে দেখতে পারি বাংলাদেশে ইনস্টল হয়ে গেছে, যদি আপনারা করতে পারেন আই ক্যান টক টু দেম।
That will be great, sir. That will be great, sir. Thank you very much.
কারণ আমি ওটার সঙ্গে জড়িত ছিলাম।
Okay, thank you for all the suggestions.
Okay. So next we go to the next speaker, that is NM6, single crystal growth and anisotropic ionic conductivity of lithium, lanthanum, titanate. Muhammad Shahjahan, Yuki Maruika, Masanori Nagao, Satoshi Watauchi, Isao Tanaka. So welcome, Muhammad Shahjahan Ali.
Yeah, thank you very much, sir and Chair. Can you hear me?
Yes.
Okay. So first of all, I would like to welcome to my presentation and good evening to everyone. National Conference on Physics 2021. My presentation title is single crystal growth and anisotropic ionic conductivity of lithium, lanthanum, titanium oxide. Actually, this work was performed at the end of my PhD work. So I want to share with you this work. This is the presentation layout of my today's talk. First of all, I will talk about why solid electrolyte is needed and research background of solid electrolyte and single crystal growth of these materials and its properties, including most important anisotropic ionic conductivity measurement, and finally I will summarize later. In the case of solid electrolyte, solid crystal batteries, usually solid electrolyte and electrodes are used, but it was started in 1950s. But unfortunately, when the metals were using silver and the conductivity was very low. You can see here that in the right upper corner, using electrolyte and the future demand of solid electrolyte materials. Also in the left lower corner, you can see that the annual lithium-ion battery demand is dramatically increasing day by day. And at the end of the 2030, it may be 2000 ZWS. Anyway, the different research team are working on the solid electrolyte materials, and you can see that the ionic conductivity of some solid electrolyte materials is almost comparable with the liquid electrolyte materials. So researchers are thinking about the replacement of liquid electrolyte materials. So why the replacement of liquid electrolyte materials? That's a very important issue. First of all, during the charging and discharging process, in the case of liquid electrolyte materials that is present using liquid materials, that have some blended formation. When charging and discharging occurs, the lithium ion deposit on the lithium ion part. As a result, the blended formation occurs, and if it is being continued to anode to cathode, then there is firing occurs. You can see in the right corner that the laptop is burning, and also airplane and some other industry is burning. So these are the issues of the using liquid electrolyte materials, which may be removed or solved by using the solid electrolyte materials in the present using batteries. Other advantages of solid electrolyte materials, you can see here in the table, is that the safety issues in the liquid electrolyte is not safe, but in the case of solid electrolyte, it is thinking that this will be safety more than the liquid electrolyte materials, and the voltage range is also in the case of solid electrolyte is in advantages. Most important things is that the cycle life. In the case of liquid electrolyte metals that is used in the batteries, the cycle life is below 1,000 cycles. But in the case of solid electrolyte, it is expected that the cycle life will be more than 50,000 cycles. And working temperature range is also different. It is also advantageous for solid electrolyte materials. And in the case of dendrite formation issues, the probability is very low. All of materials is important for the solid electrolyte materials. Researchers are saying that no, the polycrystalline materials are not safe for the battery, because in the case of polycrystalline materials, it is easy to grow the dendrite formation. So in that case, a single crystal may be the solution. Different type of single crystalline are using in the present some very small devices. Among them, The perovskite and materials are very important because its structural advantages and excellent chemical and electrochemical properties. So research background of my using materials in the University of Yamanashi, Professor Samarium worked on the lithium lanthanum oxide materials and they have found out the high ionic conductivity, and it's expected that if these materials study and grow up and used in solidated materials, then it may be used in the some light devices. So they have grown only one composition single crystalline, but my target was to grow different composition dependent, that is lithium dependent ionic conductivity measurement. You can see here that the materials preparation and the single crystal growth, and in the right corner lower part you can see the same and EDS analysis. Some single crystal are grown, but there are some crack. No inclusion, but there are some crack. And finally, we have grown some good crystal, and Xrd analysis are taken, and same EDS analysis are also observed, and no inclusion was observed. But there was some very little some crack was found. Finally, depending on the composition, we have different composition dependent crystal, and we find out that in the all cases we have find out the single crystalline materials by same and EDS analysis. During the crystal growth, the important factor is that when you use the lithium composition, the lithium evaporates. So we have measured the lithium composition, and we find out that it was almost half of the lithium was evaporated during the crystal growth, because during the crystal growth the high temperature are used, and that is 45% to 50% lithium composition evaporators are observed by same and EDS analysis and EPM analysis. You can see we have also observed AAS absorption analysis, and we have find out also almost the same result. The most important thing is the anisotropic ionic conductivity measurement. It was our main target, and we have find out the maximum ionic conductivity 1.75 10⁻³ order. And among the perovskite type materials, it is the highest ionic conductivity. And in the composition of X is equal to 0.059. It was my analysis, but previously another researcher observed it was in 0.07. We have also temperature dependent ionic conductivity to measure the activation energy, and we find out that the activation energy increases with the increases of lithium composition. So this is the summary. We have drawn different composition dependent single crystal, and we have find out that the highest conductivity yet observed 1.75 into the -3 order, which is comparable of with the liquid electrolyte. And our next target was to measure the electrochemical properties, but we have come back to Bangladesh, so we don't measure the electrochemical properties for these materials, but another materials we have measured, and we find out that some good result. So next time we will continue this work maybe. Thank you very much for your kind attention.
Okay, thank you very much, Mohammad Shahjahan, for your interesting talk. And now the floor is open for questions. Maybe one or two questions can be encouraged. So please ask questions. So there is no question. Okay, in that case, we again thank Mohammad Shahjahan Ali for his
Okay, thank you,
interesting
sir.
delivery, and we will go to the next speaker.
Thank you very much.
Okay, the next presenter is MN07, investigation of the effect of Samarium on magnetic and magnetodielectric properties of Lanthanum orthophenite nanostructures. Shobhan Kumar Kundu, Dhiraj Kumar Rana, and Shaumen Basu. So welcome, Mr. Shobhan Kumar Kundu.
Hello, can you hear me, sir? Hello.
Hello. Yes. So you can start, yes.
Okay, thank you, sir, for giving me opportunity to present my work in this prestigious conference. Today, I will be talking on investigation of the effect of Samarium on magnetic and magnetodielectric properties of lanthanum ferrite nanostructure. Currently, I am Dr. Shobhan Kumar Kundu. Currently, I am working as the assistant professor under the Department of Physics of the Department of AIUB, American International University, Bangladesh. So these are the outlines, that is contents, introductions, applications, synthesis procedure, Xrd and Rydberg development analysis, TEM analysis, magnetic properties, FC and ZS channel study, magnetodielectric properties, and conclusion. So at first I will give a short introduction. Nano, a small word with big impact. So nano is the study of the properties of material. Sorry. Okay. So properties of the materials with dimension at the nanoscale, which refers of from 1 to 100 nanometers. So the nanotechnology is the application of this nanostructure into useful nanoscale device. So in the figure, we can see that this is a nanoscale, and here we can see that this 10 to 100 nanometers range of materials can be called as nanomaterials. And nanotechnology attracts the attention of the researchers and scientists due to the in the surface to volume ratio as the particle size reduces. So what is multiferroids? Multiferroids are the combination at least two ferroic orders in the same phase. The ferroic orders are ferroelectricity, ferromagnetism or antiferromagnetism, and ferroelasticity. So in 1993, Professor Hans introduced the word multiferroid, and before that, 1996, he started a leading laboratory for study of the magnetoelectric effect and optical properties of crystals. So if we consider this is a charge and this is electrically polarizable, that is, if we apply electric field on it, and we can get polarization, and this is a spin, and if we apply, it is magnetically polarizable. That means if I apply magnetic field, then we can get magnetization. The common space is called the multiferric. Here we can tune the polarization with the applying magnetic field, and we can tune the magnetization with the applying of electric field also. So here we can also see the magnetoelectric coupling. So why rare earth materials? Rare earth materials, rare earth element market exhibits growth of 12.4% compound annual growth rate, that is CAGR, from 2014 to 2025. So it has a great opportunity to work on this. So I'm not going details because lack of time. So this is the applications of multiferric ferroelectric data storage combined with magnetic read head application, multiple state memory element application, and electric field control ferromagnetic resonance device, transducer, terahertz radiation, spintonics, etc. These are the applications of rare earth elements, and here we can see that these are the rare earth ferrite that exhibits orthorhombic structure. A is not equal to B, is not equal to C, and alpha beta gamma equals to 90. So here we can see that this large sphere, these sphere are rare earth atoms, and these sphere are iron atoms, and these spheres are oxygen atoms. So these are the synthesis procedure, top-down synthesis procedure. At first, we have taken lanthanum nitrate, iron nitrate, samarium nitrate, and citric acid as the raw material, and mixing the raw materials with in 100 ml citrate solution, and we continue stirring of 30 minutes and heating up to 70 degrees Celsius. For maintaining the pH of the solution, we added ammonium hydroxide and maintained the pH 7. So after we get a greenish color, and then we transfer it to the oven, that is hot air oven, and heated up to 200 degrees Celsius. At the last of the evaporation, it is auto-ignited, and we got the dry ash, and we transferred it to the furnace and heated up to 600 degrees for calcination. And after calcination, we with the mortar we get the fine powder like this. So these are the Xrd and ribbon repellent analysis. We can see this is for pure, and this is 1%, this is 5%, this is 10% dope. So we found that there is no impurity in this peak, and these are the that is output value for the refinement, and we can see that lattice parameter was decreasing with the doping concentration, that is A, B, C parameter, and volume size volume also decreasing, and crystallite size also decreasing, whereas a bond angle was increasing with the lattice parameter. This can impact on the magnetization process. This is the TAME analysis, and we see this is for the pure lanthanum ferrite, and the particles are almost that is spherical in shape, and 58 nanometer plus minus 2 means that is the errors. We got the errors of 2 nanometers, and 8 nanometers, around 58 nanometers, we got the particle size with the normal fitting. And here we got the this is for 10% samarium dope of lanthanum ferrite, and the around particle size is 44 nanometer. And here also we got the spherical shape in the particle size. These are the magnetic properties, and the magnetic properties we can see from the magnetic properties with the increase of the doping concentration, magnetization was increasing, and from the inset we can see that remnant magnetization was increasing with the doping concentration. And this is for 10 Kelvin result, magnetization 10 Kelvin gives us the same result. And from here we can say that magnetization of lanthanum ferrite mainly depends on the lanthanum interaction, that is lanthanum 3 plus and lanthanum 3 plus interaction, iron interaction, that is iron 3 plus and iron 3 plus interaction, and lanthanum 3 plus and iron 3 plus interaction. So if we dope samarium, samarium 3 plus and samarium 3 plus and samarium 3 plus and iron 3 plus interaction also can take place. In the dope sample, we see that the bond. Okay, madam. So in the dope sample, we see that the bond angle, bond length has decreased, which is calculated from the readable refinement. So we can this can also result in the enhancement of the magnetization. So this is the FC and ZFC property study. So from the FC and ZFC property study, we see that this is FC has been measured at 500 Oersted magnetic field, and there is a bifurcation between the FC and ZFC, and it is the that is symbol of the ferromagnetic nature of the sample. So in the magnetodielectric properties, we observed that that is the with the application of the magnetic field, the magnetodielectric property was increasing, and we got highest 0.9% increase of in the Samaria, 10% Samarium of lanthanum ferrite. So in the conclusion, nanocrystalline single phase pure and Samarium doped lanthanum ferrite has been confirmed by Xrd and Rydberg analysis. Chem study ensures that the average particle size decreases from 58 to 44 nanometer. Saturation magnetization is increasing with Samarium concentration. 0.90% enhancement in the magnetodielectric coefficient is observed in the 10% Samarium of lanthanum ferrite. Thank you for your attention. Thank you, session chair and coach for giving me opportunity. Thank you very much.
Okay, thank you very much for your presentation. Now, I think the question and answer. Anybody have any question on this presentation? Hello? Any question?
Yes, sir. There is a question. Dr. Farhad said present.
Okay.
If there is no question, thank you for giving me the opportunity to ask. You said it's nano. Did you do any selected area diffraction pattern? I'd like to see whether there is any change in the diffraction pattern, because you are showing the high resolution, I mean, bright field images. Did you do any selected area diffraction pattern?
Yes, I did it, but for short of time I have not shown in here. This is the published paper, and here I show.
Okay. Thank you.
Okay.
Okay, I have a question that what are the basis of the enhancement of magnetization with Samarium doping? Can you explain it?
Sir, actually this depends on the bond angle. In increasing the Samarium doping, we found that the bond angle was increasing, and bond angle increasing, and also bond length was decreasing. This can be the reason for enhancement of the increase of the magnetization.
What is the spin magnetic moment of Samarium from the electronic structure? For example, Samarium is which number? F, how much it is?
Sorry, sir?
The Samarium electronic state, it is I think 4
SMN 3+.
3+, okay. And this is it a 4F? Is it so? Is it 4F?
No, sir.
No.
We increasing Samarium 3+, we found that the iron 2+ was dominating in the sample. In the XP.
Iron 2+. Okay. So if there is no question, I think we thank you again for your nice presentation.
Thank you, sir. Thank you for giving me opportunity.
The next speaker is MN08, that is synthesis and characterization of zinc oxide nanoparticles and seed layers for subsequent growth of zinc oxide nanorods by hydrothermal process. presented by N.I. Tanveer, M.S. Hussain. So welcome, Mr. N.I. Tanveer.
So can you just make me unhost? That is, I
you can stop sharing now, Dr. Shubham.
I cannot do it, ma'am. Actually, this is why I'm asking for just.
And actually, you shared the.
Okay, I am leaving the meeting and then I. Okay. I think there is.
Sir,
Okay. Thank you. I got it.
Okay. Sorry. So the next presenter is synthesis and characterization of zinc oxide nanoparticles and seed layers for subsequent growth of zinc oxide nanorods by hydrothermal process. N.I. Tanveer and M.S. Hussain. So welcome, Mr. N.I. Tanveer. Yes.
Thank you. Good evening, everybody, and welcome to my presentation. At first, I'm very much grateful to my supervisor, Dr. S.F.U. Farhad, for giving me the opportunity to present this work. I myself, Nazmul Islam Tanveer, and title of my today's presentation is Synthesis and Characterization of Zinc Oxide NPS and SLS for Subsequent Growth of Zinc Oxide Nanorods by Hydrothermal Process. Before I go to the actual presentation, I would like to tell a little bit about the motivation of our present work. This motivation for selecting of zinc oxide, and we choose zinc oxide as electron conducting layer for two different applications because zinc oxide has these nice and promising optoelectronic properties. Out of all various applications, we currently focus on special synthesis of managed structured zinc oxide for all oxide solar cell. This is called all oxide solar cell because all the layer of the cell is oxide based, and there are two types of cell. One is the planar junction and another is radial junction. Actually, want to work on a radial junction, and if you want to, you can find details in our paper published in MRS Advanced in 2019. And another next application is photoelectrochemical PEC devices for solar cells, especially hydrogen, which is also very recently presented my supervisor, Dr. S.P. Farhad, in the International Solar Coil Conference in 2021, organized by RSC UK. Two, we also here this you can see the zinc oxide NRS layer, and this is why we select the zinc oxide NRS for make this type of layers. To make efficient solar cell and PEC devices, we need to grow a defect-free zinc oxide NRS with variable morphology, size, and physical properties. In our group, we successfully grow zinc oxide seeds by drop casting, salt gel technique, and spin coating technique. Here, I am focused my talk on the synthesis and characterization of high-energy ball mill derived nanostructure zinc oxide. This is materials and methods. We use these materials for synthesis zinc oxide NPS, that is zinc oxide nanoparticle, and zinc oxide seed layers for growing zinc oxide nanorods. And we completed our work by 3 steps. First step is synthesis of zinc oxide nanoparticles with high energy ball milling technique, and our milling duration is 5 hours, 10 hours, 15, 20, and 25 hours. And second step is grown of zinc oxide seed layer. At first, we disperse zinc oxide NPS in IPA, isopropyl alcohol, with 5 hours and 25 hours. Then by the spin coating, we grow the seed layer in 50 cycles, both of the 25, 5, and 25 hours. And the third step is growth of zinc oxide nanorods, and we also grow our nanorods by hydrothermal technique. And here is the procedure. I'm not going to details of this. And this is the surface morphology of zinc high energy ball mill derived zinc oxide nanoparticles. As from the surface morphology analyzed by FACM, we can see that the increasing ball milling duration, the grain size of zinc oxide powder can be reduced constantly, but for 24 hours it is increased because there is some agglomeration between the grains probably. And we get the lowest particle size for 20 hours is which is around 16 plus minus 2 nanometers. And our primary zinc powder, which is grain size is about 190 plus minus 5 nanometers. And this is the Xrd pattern of zinc oxide NPS. In Xrd spectra, here all the peaks as one plane are consist with the zinc oxide, and this is the no milling. And this from the spectra we say that we see that the peaks are broadening with increasing ball milling duration. And here the we cannot see the clearly, but it is more clear in Raman spectra, which I show the next slide. And this is the Raman analysis of high energy ball mill derived zinc oxide nanoparticles. This is the Raman analysis of zinc oxide nanoparticles. The major peaks at 35 centimeters inverse, designated as E2, is observed as Raman active phonon mode. And from the spectrum, it is clearly noticed that the major Raman peak is broadening with milling hours due to reduction of zinc oxide nanoparticles. And this is the structural analysis of zinc oxide seed layer. Here also you can see that this is for 25. This is for 5 hours milling zinc oxide nanoparticles, and for that nanoparticles we grow 50 cycle seeded layer, and this is 25 hours nanoparticles. Here also the for 25 hours the peak is broadening, then the 5 hours are seeded layer. And optical properties of zinc oxide seed layers, 5 hours and 25 hours. And left figure is the transmitters, and right side figure is the diffuse reflections. And we estimated the bandgap energy from diffuse reflection data, and our estimated bandgap energy is 3.16 for 25 hours are seeded layer, and 3.9 electron volt for 5 hours seeded layer. And this is the surface morphology of the zinc oxide nanorods. This is the 5 hours zinc oxide NRS on 5 hour milling NPS seeded layer, and this one is zinc oxide NRS on 25 hour milling NPS seed layer. From this surface morphology, zinc oxide nanorods on 5 hour milling NPS seeded layers produce large dia of nanorods around 615 plus minus 5 nanometers, and zinc oxide NRS on 25 nanometer, 25 hours milling NPS seeded layers, which is produce dense and narrower zinc oxide nanorods around 150 plus minus 10 nanometers. And these are also the cross section zinc oxide nanorods. And this is the structural analysis of zinc oxide nanorods. This is for 5 hours milling NPS seeded.
You have 2 minutes left only.
Okay, this is the 25 hours, and the first on the maximize 0.154 degree, and then this is 0.32 degree. And this structure analysis of zinc oxide nanorods, we can say that smaller crystallite size can also be seen for 25 hours zinc oxide NRS compared to 5 hours zinc oxide NRS from the Xrd product. And this is the room temperature PL analysis of zinc oxide NRS, and both samples displayed a sharp near bandage at 80 nanometer, and the band gap is around 3.26 electron volt. And this PL spectra indicated crystalline quality and the defect-free zinc oxide NRS grown on seed layer are with high energy ball milling derived zinc oxide NPS. There is some spike, but this is from the noise, which is may come from the detector. And for more details, if you want to know more details of defective zinc oxide NRS, you can be found in our published journal, also in MRS Advances in 2019. We also measured the contact angle of zinc oxide NRS with DI and deionized water and isopropanol, and the average contact angle for 5 hours NRS is 57.45 plus minus 2.2 degree, while the average contact angle is deionized water with 150.11 plus minus 2.52 degree. And where the with isopropanol, the 5 hours NRS is contact angle they show 15.17 plus minus 0.04 degree, and average contact angle with IPS 26.64 plus minus 0.2 degree. And we measured the contact angle of zinc oxide NRS for hydrophobic and hydrophilic nature with DI and isopropanol respectively, and it allows us to choose suitable
recording in
solvent for
progress.
our growing layer statements. And next, the water content angle of zinc oxide after soaking with UV 365 nanometer illumination. And this is a water contact angle of zinc oxide NRS after soaking with UV illumination, and for 5 minutes for 5 hours zinc oxide, and this is for 25 minutes, and this is for 10 minutes for 25 hours. From the water contact angle analysis, we can see that hydrophobicity of zinc oxide NRS can be controlled by illumination of zinc oxide NRS can be of UV light above the band gap energy of zinc oxide. Conclusion: zinc oxide nanoparticles are successfully synthesized by high energy ball milling technique. Defective zinc oxide NRS with variable feature are successfully grown in BMD zinc oxide nanoparticle seeded layers. Narrower and denser zinc oxide NRS are found for zinc oxide NPS for 25 hour seeded layers, and surface nature of zinc oxide NRS can be controlled by short UV exposure. Acknowledgement. I'd like to thank to acknowledge the Biomedical and Toxicology Research Institute, BTRI, BCSIR, and all the scientists of BCSI laboratories, Dhaka. This is our sponsor, the World Academy of Science and the Royal Society of Chemistry. Thank you. Thank you, everybody, for patience here.
Okay, thank you, Dr. Tanveer. I think it's a very interesting lecture that you can control the morphology by just changing the procedures. So, just I will give floor to the others. So, any question for this presentation? Is there anybody who can who is interested to ask some question to? Okay, then in that case, I have a small question that from the application point of view, you have shown that your material have the capability to be super hydrophobic and as well as super hydrophilic. Is it so?
Yes, sir.
Okay. The controlling parameter, what are the controlling parameter? I forgot maybe.
Sir, there we soaking with UV illumination, UV light.
Okay,
UV light
that should have an energy higher than the band gap of the
Yes, sir. Zinc oxide. Zinc oxide.
zinc oxide, which is 3.27. Is it so?
Yes, sir. Yes, sir.
So short wavelength UV light.
Yes, sir.
You have written already 365 nanometer wavelength. Huh? Okay.
Yes, sir.
Then what was the substrate you use for this coating?
Quartz
Quartz
glass.
Quartz
Quartz glass, SLG.
Quartz glass is the expensive. Normal glass you have tried, for example, normal.
Yes, yes, sir. We also tried on SLG glass, soda lime glass.
Okay. And what was the thickness of the film?
We didn't measure yet for the corona pandemic, and
probably this is a very important parameter that
yes, sir. Yes,
because it is another controlling parameter, the thickness. So
yes, sir.
you have to go for the measuring the thickness dependent this hydrophobicity and hydrophilicity, and at the same time what is the cohesion and adhesion. Some of the then stress develop substrate and the material coated, so that there should be a matching of these two things for a good adherence and coherency. So from the application point of view, there are more things to be done. We do not claim here, but
if we want to throw another layer on zinc oxide nanorods, and for which solvent is suitable for us, and this point of view, we actually want to say the contact angle of zinc oxide nanorods.
And then again, it comes that this is a columnar growth of the nanorod. Is it so? Columnar growth, because zinc oxide is a anisotropic property that grows vertically. So maybe the diameter of the growth, aspect ratio, these are the things that that needs to be studied also in more detail.
Yes, sir. Yes, sir.
Okay. Anyway, so thank you very much for your presentation. So now we'll go to the next speaker, which is probably the last one. So maybe Dr. Maria can take care of it. MN09. Our co-chairman, Dr. Maria. Yeah.
Are you leaving?
Yes, 09.
09, sir. He's not present, maybe because I couldn't contact him.
Oh.
MZ Hossain. Are you there?
This is, yes, Khatun, Saidul Islam. Structural and improved dielectric, electrical, magnetic properties of DFU and nickel, copper, cadmium nanocomposites. MZ Islam and Belal Hossain. So absent, huh?
Probably maybe the organizing committee can confirm us. Nuzul bhai, is he here?
The last speaker,
Belal Hossain.
Belal Hossain and MZ Islam. So he's not present.
We are not found him.
Okay.
I couldn't find him in the chat box and the participant list actually.
Okay, then at the conclusion, so Nuzrul, yeah, নাই বোধহয় নাকি? ঠিক আছে. So if the presenter is not present, so I think this is the end of the session. And I like to give a very short comment on the whole session, that the topic of nanomaterials, of course, it is one of the most interesting and very attractive topic for the young scientists. So we have many contributory papers, and I can tell one thing, that I have been working with this type of research and interested also for a very long time, but I'm very much pleased that recently the quality and the experimental methodology techniques and data presentation, everything has increased and has developed quite a lot. They have learned how to use a lot of sophisticated state-of-the-art equipments for characterizing the material. And recently, I can tell you that Bangladesh is blessed with a lot of unique facilities like EM, ACM, FPACM, XPS, including Raman, FTIR, and they are all of them are working and have very good condition in different places. The thing is that less cooperation and less collaboration is working. I think this conference indicates that people have enthusiasm, they can work very good and get some very unique results, provided we can expand the utility of these sophisticated equipment that we have in Bangladesh, that different people can use it, and how it can be used. I do not know. That these things should be discussed sometime through the physical society, that how people can get entry into the different laboratories, and what should be the way and basis for that. And I will not say that this paper is good, this paper is no. I tell you that almost every paper is very good. Each and every paper has its own unique things. They have tried to explain a lot of science and a lot of fundamental basis of many interactions, including very well characterization mechanisms from home and abroad. They have worked. So I find it very interesting that things are developing in Bangladesh, and our young, brilliant minds are getting more capable and more enthusiastic than before, I think. So I request our co-chair, Dr. Maria, who is also very close to me, and we have been working for a very long time. So I will be happy if Maria say a few words in connection with the all presentations that she feels like. Welcome, Maria.
Thank you, sir. Actually, the session was very interesting and well representative. But a few of the things I would like to suggest that the process of our research in Bangladesh remain the same. What I did the last 12 years ago, and the same things is happening in the lab. Now we should move to few of the things in the application sense, not only on the basic physics. We have to mix the physics that what we did in the laboratory, is it work in the real life or not? I think we should focus on that also. And,
yes, thank you. Very good, yes.
And personally today, I feel that, am I allowed to say this, that which one I like the most?
No, maybe we will not disclose it at the moment, but because we two together will join, because you have a marking or something. We'll see, and then finally we'll say, because we have not checked the one.
It will be announced on
Anurul?
We have to announce, right?
No, I think
today, it will announce tomorrow.
Yeah.
Okay.
What
announce করবো, announce and closing session.
Yes, exactly. So Dr. Maria said that yes, physics is the basis and basic to the engineering. So the physics as education would be reflected in the practical work, where we are lacking. As she was saying that what we were doing before 12 years. Yes, now a lot of research I saw that is why I was asking that how this material applied. There are a few materials that are very encouraging, like hydrophobic material, like the energy storage systems, like some dielectric, multiferroic, which is a big prospect in the future. So we have to gradually try to make some small devices and to see how their work performance or how they are working invariance with the temperature, like one work we are saying that is room temperature. Yes, we have to look into room temperature plus minus 20 degrees so that we can see that the device can work in hot weather or cold weather. So these are the things in future will be developed, I think. So I again stress the comment of Dr. Maria that really we want some application of physics. What we are learning, we have to apply it. Then physics education will be very, very suitable and will be capable to serve the nation in the exact way as it should be. It is the basis of all sciences, I think. So physics should go ahead with its basic understanding and the applications understanding so that physicists can stand as a pillar for developing science and technology in Bangladesh. Thank you very much.
Thank you.
So maybe we can now
Conclude the session.
we can in conclusion we can say that we can finish here. And we are very happy that a lot of technical group that have assisted us. Otherwise, we will be handicapped. I was out of the internet for some time, some 5 to 6 minutes. So these are the problems we face. But anyway, we have finished it finally in a good way. So thank you all. So this session is declared as closed. So if Nazrul, think we are finished.
Sir. Actually, নজরুল ভাই ওই যে ইলেকট্রিসিটি চলে গেছে তো স্যার আমি একটু বলি আজকে তো ক্লোজ হয়ে গেল আগামীকাল সবাইকে একটু আমন্ত্রণ জানালাম সবাই উপস্থিত থাকবেন আগামীকাল সকাল 9টায় শুরু হবে আবার আমাদের সেশন so thank you all and we have learned a lot of things lot of physics and we will apply in our research. And tomorrow I request all please be with us tomorrow in the tomorrow sessions. Thank you very much, sir.
Okay, thank you. আচ্ছা মারিয়া আমার একটু পরে ফোন দিও কেমন একবার তোমার সঙ্গে কথা শেষ করে ফেলবো তখন আমি ঠিক আছে ওকে বাই
Okay.